Dear students, today we are going to discuss behavior of a conductors in electrostatic field. So, we'll see that how the electric conductor that behaves when it placed in an electrostatic field. So, in this series, first of all we have net electric field inside the conductor is 0. Or you can say the net electric field in the interior of a conductor is 0. So for this we can see here this is electric field E applied across these two ends, and a conductor is placed in between these two ends. Then we find that these induced charges are produced in opposite order as in opposite to the applied electric field, and this induction is continued, or you can say the flow of electron is continued against the electrostatic field till the electric field inside the conductor becomes 0. So therefore at particular instant E equal to E external minus E induced equal to 0, means when induced field is equal and opposite to the applied field, the electric field inside the conductor is 0. Then the second one we have you can say that just outside of a charged conductor, electric field is normal to the surface. What is here? Just outside of a charged conductor, electric field is normal to the surface. So here you can see that electric field just outside the surface that always remains normal to the surface. So you can see, because we have already discussed that electric field just outside the surface, electric field just outside the surface is normal to the surface. So here we know that E dot dl, that is at the surface it is 0, because the tangential component of electric field is always 0 at the surface. So if it is 0, then you can see that E is perpendicular to the dl, means we can say that electric field is perpendicular to the surface. Then the third one, that is net charge in the interior of a conductor is 0. Net charge in the interior of a conductor is 0, and any excess charge resides on its surface. Means excess charge means the free charge is available in a conductor, they always resides on the surface. The interior of a conductor, the net charge, or you can say the free charges, or you can say the excess charge is always 0. So for this, you can see that this is suppose a conductor, the whole charges are residing on its surface. If you are going to consider a Gaussian surface just inside the outer surface of a conductor, then here from the Gauss theorem, that is electric flux equal to E dot ds equal to Q upon epsilon naught. This we have discussed earlier. Then inside the conductor, you know E equal to 0, electric field is always 0 inside a conductor, as we have discussed in the first point. So here E equal to 0 means flux equal to 0, or if flux is 0, then from Gauss theorem the net charge is 0. Okay, so in the interior of a conductor, the net charges is always 0 as electric field is 0. Then the fourth point, that is potential is constant within and on the surface of a conductor. Electric potential that remains constant inside a conductor as well as on the surface of a conductor. That can be proved by taking this relation. This is relation between the electric field and potential gradient. So from this relation we can say that inside a conductor E equal to 0 Therefore, dV upon dr equal to 0 or change in potential equal to 0 means V constant. So, inside a conductor, electric potential is always constant, inside or at the surface. Then, in the fifth point, next we have electric field at the surface of a charged conductor. Electric field at the surface of a charged conductor is proportional to the surface charge density. So surface charge density, you know, the surface charge means the charge at this per unit surface area, that is surface charge density. So to electric field is always proportional to the surface charge density. That we can prove by considering this is suppose a conductor. And at this conductor, we just consider here a small surface element, that is del S. And by taking del S, we just assume a cylindrical Gaussian surface. In this cylindrical Gaussian surface, E, that is always remains outward, that is normal to the surface, and same as the area vector that also along the electric field. So the dot product of these two, area and the electric field, is E del S, and from the Gauss theorem, this is Gaussian surface, and from the Gauss theorem, phi E equal to E del S equal to Q upon epsilon naught, or Q, that is charge. From the surface charge density expression, we know already that sigma equal to Q upon del S, total charge upon surface area. So this is surface charge density. Or from this you can see that Q equal to, you can take here sigma del S. So here phi E equal to E dot ds equal to Q upon epsilon naught, or Q equal to, we can take here sigma del S. Therefore E dot del S equal to sigma del S upon epsilon naught. This del S, that is cancelled out, and we will get here E equal to sigma upon epsilon naught, or E is proportional to sigma, means E is proportional to surface charge density. This is we have proved as we have required in this point. Then the sixth point, that is also very important, electric field is zero. Electric field is zero in the cavity of a hollow charge. Electric field is zero in the cavity of a hollow charge of a conductor. So this is suppose a conductor, and you know we just going to consider this is a cavity, and inside the cavity electric field inside the conductor, that is always zero, we have proved earlier. So here in the cavity, that also exists inside in the interior of a conductor. So that is also E equal to 0. It means Q equal to 0 because there is no charge inside a conductor. So there will be no electric field inside the cavity of a hollow charge conductor. So this is what we have discussed in today's topic, the behavior of a conductor in the electrostatic field. Thank you.